Hi, my name is Andrew Dillon, and today I am here with Nathan and Nicholas, and today we will be going over Project 2 for Physics 212. We decided to do the second project topic, which was the buoyant force example, where it stated that an object that is immersed in a fluid will then experience a force that is an upwards force due to the pressure of the displaced fluid, which is known as the buoyant force. Throughout this video, we will be constructing a model for this force, and we will be using this to explain different real-world phenomena that use this force to function in everyday life. As you can see here, for this example, we will just be using a basic submerged object inside of a fluid. For this one, we'll just say water right here. This one will be water, and then we can somewhat see here that we could easily just draw a free body diagram or an extended free body diagram that we have covered extensively in Physics 211 and 212, where we have a downward force for the acceleration due to gravity here, but we will only have an upwards force, which is the buoyant force right here. We can then also see that the equation for the buoyant force would just be rho, the density, times gravity times the volume of the fluid, while density will also be the density of the fluid. That this is known as Archimedes' principle. We can also see from this that it is also slightly different because this is now covering more into the topic of different densities, which we have slightly covered earlier when talking about inertia earlier in this term. The other thing that we do need to take into account for are the limitations of this model. We can see the limitations that we could assume there are limitations because we are still not sure, as we have not covered this in class, about the fluid densities and how it would pass through multiple fluids. Say in this model right here, we have water right here, and then we also have it as it goes down in a tube. We would also have oil right here. Oil and water will have different densities, so now we will be considering how to separate each different fluid into its own different equation to solve for.
In order to adapt this project to our physics model, we determined the best course of action to explore this topic is with Archimedes' principle. Archimedes' principle is based on the idea that buoyant force of an object is equivalent to the density of the fluid times gravity times the volume of the object, which is also equivalent to the weight of the fluid that it displaces. Now, do not mistake fluid to only mean water or a liquid here. Another physics model that we'll have to consider is the model of fluids. Fluids here are considered as substances that flow, or substances that take the shape of their container. This definition also considers gases, such as air, since they similarly take the shape of the container that they are placed into, like liquids. Solids, however, are not considered a fluid here because they do not flow. They retain their form with a fixed volume and shape, and do not take the shape of their container. With these physics models in mind, we can apply this knowledge to a fully submerged object, where we can then construct a free body diagram as such. What we have here is two force values denoted as force 1 and force 2 that act on the top and bottom of the object submerged. Each force value is determined by the respective pressure and area of the surface they act on. This can further be broken down into the height times density times gravity times area of the respective force value. Now, to determine the buoyant force, all that's left to do is to take the difference between the second force and the first force. So what can we interpret if we are just given the value of the buoyant force? Well, we can settle it down to three results. If the buoyant force is greater than 0, force 2 is greater than F1, which means the object will rise within the fluid. If the buoyant force is 0, force 1 and force 2 are equal to each other, which means the object will neither float or sink in the fluid. Lastly, the buoyant force is less than 0. If it has a negative value, the object will sink from its current position into the medium. In summation, buoyant force is the difference between force 1 and force 2, which is equivalent to the weight of the fluid that it displaces. I will now leave the sense-making section to our project to Nathan Ching.
We'll do some sense making now for the equation for force of buoyancy. So we know that force of buoyancy is equal to density of the medium times gravity times the volume of the object. So we know that density for the units of density is going to be kilograms per meter cubed. Gravity will be meters per second squared as we learned earlier. And then volume will just be meters cubed. So we have meters cubed in the numerator and then meters cubed in the denominator to cancel off. And we're left with kilograms meters per second squared is equal to kilograms meters per second squared. Yeah, so we have made one example. It's a cylinder inside of a body of water. So quick Google search, we can find that the density of water is going to equal to 1 gram per milliliter. So about 1,000 kilograms per meters cubed. And then as we plug in our defined volume, we can use our numbers here for radius and height. So we have 0.05 meters squared times pi times the height of 0.2 meters. It's going to be about 0.00157 meters cubed. When we plug in all our numbers, we'll get 1,000 kilograms per meters cubed times 9.8 meters per second squared times 0.00157 meters cubed. And we'll find that our force of buoyancy is 15.394 kilograms meters per second squared. Then if we come over here and we look at a free-body diagram, we'll notice that our force of buoyancy is much greater than the force of gravity. So for the cylinder to stay in place here, there must be another force, say like a fan pushing down on the cylinder, making sure it doesn't float up. Then if we come and look at another example of a balloon, say floating in the air or stationary in the air or something, we can do a quick Google search. We'll find that air is 1.29 kilograms per meters cubed. And so our volume will be 4/3 pi cubed. Our radius will be 0.1 meters. Plug that in, and we'll find that the volume is 0.0141 meters cubed. We plug in our values again, 1.29 kilograms per meters cubed times 9.8 meters per second squared times 0.0141 meters cubed. We'll find that the force of buoyancy for the balloon is 0.179 kilograms meters per second squared. And once again, we come over and look at our free-body diagram. The force of buoyancy is much less than gravity. So there must be another force that is pushing up. Would explain why balloons float in the air. And that will likely be because the balloon is filled with helium, which has a less density than air. And that will cause the balloon to float up more instead of dropping to Earth as this free-body diagram would make it seem like. And then if we compare these two situations, we'll see that because density of water is much greater, almost 1,000 times greater than density of air, then as the density increases, then the force of buoyancy will increase and checks out because we have a force of buoyancy of 15 versus the force of buoyancy of 0.17 in the balloon scenario. So we can see that this relationship makes sense and opposite will be true. So as the density decreases, the force of buoyancy will also decrease. And that would be the end of my sense making.
Hi, my name is Andrew Dillon, and today I will be doing the explanation and the different examples of real-world life and phenomena that we can see using buoyant force. For our first example, we will be looking at an object submerged in a fluid that is water, and then we will be looking at an object submerged in a fluid that is a type of air. For our first example, we will be looking at a shipping container and a pebble with both mass m are put into a body of water, and as we can see, the pebble would sink while the boat would float. And the reason of that is, if we look at the length of the boat, we can see it's 1000 L, while the pebble is just 0.01 L. These aren't true accurate values, but they are enough that we can accurately convey what we are trying to see. Because the boat is so large, it will have a greater dispersion of water that will allow it to float, because as long as the weight of the water that is dispersed by the ship will be greater than the weight of the ship, it will float. While for the pebble, because it takes up very little space, it will have very little water dispersion. So the weight of the pebble will be greater than the weight of the water dispersed, causing it to sink. However, for the boat, as we can see, if we would keep adding different weights to it, say more shipping containers, eventually there would be a point where the total weight of the ship would then be greater than the weight of the water dispersed by the ship, causing it to sink. Likewise for the pebble, if we were to reduce the mass of the pebble, say divided by 1000, we would then see the pebble begin to float, or if we took a significant portion of the weight, so as long as the weight of the water dispersed by the ship would be greater than the weight of the ship. And now for our second example, where an object is submerged in a fluid that is air. For our example, we decided to take a look at the balloons, specifically the Thanksgiving Day parade balloons, where they are extremely large and they still manage to be able to float. Because we looked at buoyancy from the previous example where as long as the density of the water displaced by the ship would be greater than the total weight of the ship, we can use that same exact thing for our example here, whereas we would pick a lighter and less dense gas such as helium, rather than just take air out from the surrounding area in our atmosphere. We would allow the balloons that are hundreds of pounds to be able to float, because of the less denser gas inside the balloon would be wanting to go up. And if we were to instead fill it up with normal air, we would then see equally dense gas inside the balloon and outside the balloon. So they would be the exact same, causing the weight of the balloon to want to fall back down, where it would do so, albeit very slowly.